Hello students, today I will start the new chapter in the fourth model, that is the force convection. And already we know that force convection means when the fluid motion is induced by artificially, then we'll call that is a force convection. That motion is induced by either blower or a pump or fan, okay, which forces the fluid over the heat transfer surface is known as a force convection. And for the force convection, here whatever the heat transfer rate is there, that we have to find. To find the rate of heat transfer, we should find out the first heat transfer coefficient. Then the heat transfer coefficient, whatever is there, it is having the sum with the correlation with the some of the parameters, okay, of the that both the heating surface as well as the fluid properties. For that purpose, here now we have to use the dimensional analysis to find the apply to the force convection correlation we have to use. From that we can find out the heat transfer coefficient, and later that is useful in the different equations to find the heat transfer rate by using the different conditions. Okay, for that the dimensional analysis for force convection is correlated by Nusselt number is equal to function of Reynolds number and Prandtl number. Okay, here the different variables specifying the system behavior, okay, shown in the figure, which represent the force of convection of the fluid flow over a flat plate. Okay, here the different variables what are to be considered for the force of convection, those are represented in this figure. Okay, those whatever the variables are there, that is the surface temperature, heat transfer coefficient, velocity of the fluid, the dimension, there is a length of the that flat plate, and the fluid temperature as well as its the fluid viscosity we have to take, and its density, specific heat, all these here we can show that one. The new rho k Cp, thermal conductivity of the surface, all these things variables we have to consider for the analysis, that dimensional analysis. This dimensional analysis is a Buckingham's pi theorem. That Buckingham's pi theorem, from that one the different pi terms we have to find out, and later we have to correlate that one to find the our desired equation. As a dimensional analysis variables for force of convection, these are the dimensional analysis. The dimensional less numbers what we have considered, that is a Nusselt number is a HL by K, Reynolds number now is rho LV by mu. Okay, Prandtl number is a mu Cp by K. Hence the heat transfer whatever is there in this one, the heat transfer coefficient, that is represented as the function of the different variables. The heat transfer coefficient is a function of density, length, velocity, viscosity, specific heat, and thermal conductivity. Or this equation we can write as a function of H rho L phi mu Cpk is equal to 0. This equation will take as a 1. And in equation 1 there are number of variables are what we consider for the force convection. These are the 7 number of variables. Then fundamental dimensions what are there? The fundamental dimensions, already we know that there are 4 fundamental dimensions. The 4 fundamental dimensions are here we have taken number of fundamental dimensions 4. That is a fundamental dimensions. Quantity dimensions or quantities we will call as a mass m, length L, time t, and the temperature theta are considered as fundamental quantities. Then this number of variables minus of the fundamental dimensions, that will give the number of 3. Those are called as the pi variables. Number of pi terms. There are 3 pi terms. There is a function of the 3 pi terms, that is a pi 1, pi 2, pi 3 is equal to 0. And here the pertinent variables in the force of convection heat transfer, the pertinent variables, the what variables we have considered and their dimensions we have to take here. And first we will take the slab length, okay, that is a tube slab dimension, that is a characteristic length. We will take length L, and that length already dimension also in terms of the length. Then fluid density, though rho, that is a kg per meter cube, kg is a mass, and meter cube, that is a length cube, ml raised to minus 3. Fluid velocity meter per second, that one, that is a length per time, that is a L T raised to minus 1. Similarly, fluid viscosity, that will get, that is all substituting all the viscosity dimensions. Okay, then we are going to get the finally simplifying the ml raised to minus 1 t raised to minus 1. For the specific heat Cp, we are going to get the dimension as L square t raised to minus 2 theta raised to minus 1. For thermal conductivity, ml t raised to minus 3 theta raised to minus 1. And coefficient of heat transfer, convective heat transfer coefficient H can be written as m t raised to minus 3 theta raised to minus 1. Then here we have to take from the equation 1 number of repeating variables. Okay, from the equation 1 repeating variables we have to take. There are 4 repeating variables we have to consider by considering the different properties. One is a chemical property, one is thermal property, one is physical, and another one is a flow property. Here the chemical, the mu viscosity we have taken, and the thermal property, thermal conductivity K we have taken, and dimension property or a physical property, length we have taken, and the flow property, that is a V. By considering here 4 we have to take that one. All the 4 properties we have to consider. One is a chemical, thermal, dimensional or physical, and the flow property. All these 4 we have to consider here. And these are the 4 m, k, l, v. These are the repeating variables. And by taking all these repeating variables, the pi term can be written as the pi 1, the first pi term, that is the pi 1 is equal to mu raised to a1, k raised to b1, l raised to c1, v raised to d1 to rho. Here, after taking this mu, k, l, v repeating variables, the 3 variables are remaining. Okay, the 3 variables rho, cp, h. Okay, one by one we have to take those variables along with this one. Okay, that is rho, that is equal to m raised to 0, l raised to 0, t raised to 0, theta raised to 0. That is equation 2. Now we have to substitute the dimensions of mu, k, l, v, rho, and we have to equate to this right hand side. Okay, the mu dimensions are m, l raised to minus 1, t raised to minus 1 raised to a1, then k, m, l, t raised to minus 3, theta raised to minus 1, b1 raised to b1, and l raised to c1 for this l only, v is l, t raised to minus 1 raised to d1, and this rho is m, l raised to minus 3, that is equal to m raised to 0, l raised to 0, t raised to 0, theta raised to 0. Now comparing the powers of the m, l, t and theta, or indices of the m, l, t and theta on both sides, left hand side and right hand side, we have to compare to find all these powers. Okay, for that one, for the m, okay, for the m comparison of the power, here m raised to 1 is there, then a1 we have to take. M raised to 1 is there, then b1 if you multiply, that's b1 plus of b1. Here m term is not there, here also m term is not there, here 1 is there, m raised to 1 plus of 1. This side the m raised to 0 is there, then equate this one. Okay, then this equation we can write as again for the m, a1 plus b1 is equal to minus 1. Then for comparing the term powers of the L, okay, comparing the powers of the L raised to minus 1 is there, then it becomes a minus a1. Okay, L raised to plus 1 is there, then plus of b1 will get. L raised to 1 is there, plus of c1 here. L raised to 1 is there, plus of d1 will get. Okay, here L raised to minus 3 is there, minus of 3, that is equal to L raised to 0. Then comparing the powers of the T, okay, here t raised to minus 1 is there, minus a1. Okay, here t raised to minus 3 b1. Okay, here t term is not there, here t term is there, minus d1. Okay, here there is no t term, and here t raised to 0, that is equated to the 0. Comparing the powers of the theta, okay, that is here there is no theta, and here minus 1 is there, theta raised to, that is minus b1, and there is no theta term here also up to, and there is no theta term, that is equated to the 0 only. Then minus b1 is equal to 0. Okay, then solving these equations to find this a1, b1, c1, d1. Okay, for this one the first we will get that is b1 is equal to 0. b1 is equal to 0. Then this b1 is equal to 0 if you substitute in the first equation. This b1 is equal to 0. Then a1 is equal to minus 1 we are going to get. Then a1 and b1 we know. The third, this t powers, if you a1 and b1 if you substitute, d1 we are going to get. This is minus of minus 1, that is plus 1. Plus of this term will be 0, minus d1. Then this one minus d1, if you send this side, this becomes a 1. Then d1 is equal to 1. And all a, b, d if you substitute in this equation, that is the L powers equation. This is minus of minus plus 1. This is 0 plus of c1. This is d1 is 1 minus 3. Okay, here 2 plus are there. Plus of c1 minus 3 is there. Then this becomes a minus 1. Okay, d1 c1 minus 1, this becomes minus 1. If you send this side, that is also plus 1. Then c1 is equal to 1. Then here all the powers we got here. That is a1 is equal to minus 1, b1 is equal to 0, c1 is equal to 1, d1 is equal to 1. Then substituting this in equation 2. In equation 2, if you substitute, we are going to get mu raised to minus 1, k raised to 0, l raised to 1, phi raised to 1, rho. Okay, the rho we are getting. Then here first pi term, pi 1 is equal to, here that is a L, rho L V is there, that is in the denominator, k raised to 0, that becomes 1. Then mu raised to 1 is there, that is taken into denominator. Then rho LV by mu we are going to get. This rho LV by mu is a Reynolds number. This is equation 3. For the second pi term, here the pi term, pi 2 can be equated to mu raised to a2, k raised to b2, l raised to c2, phi raised to d2, cp that is equal to m raised to 0, l raised to 0, t raised to 0, theta raised to 0. That equation 4. Here substituting all the dimensions again. Substituting all the dimensions in this one. Okay, here the secondary cp is taken. Okay, in the remaining variables, in that second one is cp. Then that is equated to the 0. Okay, that is equated to the indices of the all the variables 0. Fundamental dimension 0, that is equated powers. Then comparing the powers of m, l, t, theta on both sides. For m, a2 plus a2, okay, plus b2. Okay, here there is no m term, that is equal to 0. Then L for that one, minus a2 plus b2 plus c2 plus d2 plus 2, that is equal to 0. Then for the t, minus a2, okay, minus 3b2, okay, minus d2 minus of 2, that is equal to 0. Then for the theta, okay, there is no theta term in the first, and second minus b2, and there is no minus b2 minus of 1, that is equal to 0. Therefore this is b we are going to get as a minus 1, b2 minus 1 we are going to get. Minus 1 if you substitute in the first equation, a2 is equal to 1 we will get. Then similarly d2 and c2 after substitution we are going to get as a 0, 0. Then the whatever this phi 2 term in the equation 4, if you values all these values, if you substitute, then pi 2 term, whatever this one equation 4 in this substitute these indices, these two terms become 0. Mu k we are going to get, that is a2 b2 both are b2 is mu cp by k we are going to get. Mu cp by k, that is a fifth equation. Mu cp by k is a Prandtl number. Then for third phi term, that is again we will substitute all the repeating variables, some their indices, and h variables we have taken in the third pi term. Then that is equated to the these dimensions raised to power 0. This equation 6. After substituting this whatever the dimensions of this mu k lb are there, then equated to the 0. Then comparing the powers of m, l, t, theta on both sides. Okay, similarly here m a3 plus of b3, okay, plus of 1, that is equal to 0. Like this for L also we are going to get minus a3 minus 3b3 plus c3 plus d3, that is equal to 0, and t minus a3 minus 3b3, okay, minus 1 minus d3 plus of 3 that is equal to plus of 1 that is equal to 0. Okay, then B3, in this one B3 is there, B3 minus of 1 is equal to 0, and here we are going to get B3 is equal to minus 1. After substituting B3 is equal to minus 1, A3 is equal to 0 we are going to get, and A3 0 if you substitute here, B3 is equal to minus 1. Okay, then this is 3 D3 we are going to get the 0, and substituting in the L power indices, C3 is equal to 1 we are going to substitute. Then substituting all these indices in equation 6, we are going to get the here B minus 1, the K in the denominator should go, C3 that is 1, okay, this L by that is HL by K we are going to get, HL by K, that is the Nusselt number. This is the equation. According to Buckingham's pi theorem, okay, the function of the all the 3 pi terms is equal to 0, or we can write a pi 3 is equal to function of pi 1 and pi 2. Then pi 3 whatever is there, HL by K, that is a function of the rho LV by mu Cp by K, that can be written as Nusselt number is equal to function of Reynolds number and the Prandtl number. This is the analysis. Okay, Buckingham's pi theorem or a dimensional analysis of a force or convection. And this equation what is there, that we can in practice above equation, this equation here can be written as Nusselt number is equal to constant, Reynolds number raised to some constant, and Prandtl number raised to some constant, where A and B evaluated experimental. These are experimentally evaluated for the particular cases. Okay, then this later we will take this one. Equations are there in this, that referring equation 9 whatever is there, which is can be written as Nusselt number is equal to C into some constant instead of function, that is a constant we have taken, then Reynolds number raised to n, m, Prandtl number raised to n. Then value of C, m and are correlated for the different flow conditions and different geometric configurations, and few of them listed below here. The first one, flow of the fluid over flat plate at constant temperature. At constant temperature, we are going to get this equation. Nusselt number is equal to 0.664 Re raised to 0.5, Prandtl number raised to 1 by 3. This is the equation for this particular case. Okay, then equation is valid for the laminar flow. That is the Reynolds number is less than 2 into 10 raised to 5. If it is a more than 2 into 10 raised to 5, then that becomes a transient, turbulent flow, and that can be equation is different for that one. For the partly turbulent, okay, here the partly turbulent for that one. In this one, partly laminar and partly turbulent. Okay, there is a transition region, and for that transition region, okay, laminar turbulent region, the equation we are going to get here. Nusselt number is equal to 0.036 Re raised to 0.8, Prandtl number raised to 1 by 3. That is equation. Okay, where Re is greater than 2 into 10 raised to 5 and less than 10 raised to 7. And here all the fluid properties we are going to determine for the average temperature. That is the fluid temperature and plate temperature divided by 2. That is for the mean temperature, all the properties we are going to determine. If the fluid is flowing inside the tube over the annulus, okay, or over through the annulus, inside the tube or through the annulus, if the fluid is flowing, okay, that is inside flow of the fluid. For that we are going to use the Nusselt number equation as a 0.023 Re raised to 0.8, Prandtl number raised to 0.4. Okay, where Reynolds number is greater than 2300 and less than 12 into 10 raised to 4, and this is and Prandtl number is between 0.7 to 120, and L by D ratio less than 60 for that particular pipe. Then properties again we are going to determine as a surface temperature and the mean temperature of the fluid divided by 2 we are going to get. Like this, again for laminar flow, local Nusselt number we are going to find out by using this thing. Average Nusselt number we are going to get as a 0.664, twice of this one if you have the average Reynolds number. Then friction coefficient CFX we can going to get as a 0.664 into Reynolds number raised to minus half. Okay, like this, in terms of the Stanton number also we are going to get, that is the 0.332 Re raised to minus half, Prandtl raised to 2 by 3. Okay, in terms of the Nusselt number and the Prandtl number, this coefficient of friction we are going to get as a Nusselt number. These are local coefficient of friction, that is a Nusselt number Re raised to, and this equation Rex and Prandtl number X, that is X means it is a local Cfx by 2. Heat transfer from the hot surface, okay, flowing through the flowing gas, that we are going to get this 0.37 Re raised to 0.6 and this one. And here these different dimensional numbers we are considered, Reynolds number and Prandtl number and also Nusselt number, okay, Stanton number. These 4 numbers are the dimensionless number, and these dimensionless number, what are there, what is their definition as well as physical significance, we have to know here in this stage. Okay, to know that one dimensions already definition, Reynolds number definition is the inertia force to the viscous force. Already we know that one. Okay, that can be given as, okay, VL by nu, okay, rho VL by mu. That one, anyone we can find out from this one. And here Reynolds number, what is there, okay, that is we have to take, that is available from the data handbook. It is available in the data handbook definition, but physical significance we should know that. Reynolds number is used to determine the change from the laminar to the turbulent. Already we know that one. The Reynolds number is used for finding the laminar and turbulent flows. Okay, how the change in the laminar and turbulent flow is there, that we can determine from the this Reynolds number. The Reynolds number is less than 2 into 10 raised to 5, that is a laminar flow. If Reynolds number is more than 2 into 10 raised to 5, that may be a transition or a turbulent flow. And Prandtl number, the Prandtl number is defined as the ratio of molecular diffusivity of momentum to the molecular diffusivity of heat. It is represented as energy transport by the diffusion process. Molecular diffusivity of momentum to the molecular diffusivity of heat. It is the energy transport it will determine. That is mu Cp by K, and that was nu by alpha also. In that way also we can determine. And Prandtl number is equal to 1 for gases, and it is greater than 1 or equal to 1 for oils. Okay, always less than 1 for the liquid metals. Okay, then the another 2 numbers, there is a physical significance of Prandtl number, the development of velocity and thermal boundary layers for the flow along flat plate, and their magnitudes depends upon the magnitude of Prandtl number. Okay, that is a velocity and thermal boundary layers, whatever the development and their magnitudes are there, that will be depend on the Prandtl number. Okay, it is a velocity and boundary layer concept, that one Prandtl number will gives. Nusselt number is defined as ratio of heat transfer by convection to the conduction, okay, across the fluid layer and of thickness L. Okay, convection heat transfer to the conduction heat transfer, that is a Nusselt number. A large value of Nusselt number means heat transfer by convection is more. Okay, that is a numerator is more than the denominator. Okay, the convection heat transfer will be more than the conductive heat transfer. Then Nusselt number is equal to 1. Okay, that is heat is transferred purely by conduction. Okay, if it is 1, then heat is transferred purely by conduction. Nusselt number is convenient measure of the heat transfer coefficient. It is a convenient measure of the heat transfer coefficient. This Nusselt number always will use for finding out the heat transfer coefficient. As we know in that whatever the boiling and condensation chapter also, we have discussed the heat transfer coefficient we have to determine by using the Nusselt number correlation only. Here also there is a convenient measure of the heat transfer coefficient. It relates a convective surface coefficient to the thermal conductivity of the fluid. The another number is a Stanton number. The Stanton number is defined as a ratio of heat flux of the fluid to the heat transfer capacity of the fluid. Okay, heat flux of the fluid to the heat transfer capacity. Okay, heat flux of the fluid to the heat transfer capacity of the fluid. Okay, the H by rho Cp um. Okay, um is a mean velocity, that is physical significance. It is correlated to forced convection only because of it contains velocity. It correlates because of the velocity term it contains, velocity of pulp. It is used as a characterize the heat transfer in forced convection. Okay, it is used to characterize the force convection heat transfer. Heat transfer into the fluid to the thermal capacity of the fluid. Okay, these are the different non-dimensional numbers. Here directly all these non-dimensional numbers are available in the data handbook, or you should know that their definitions, and later their physical significance you have to define it. And I will continue in the next class with the